Yes, hi. Hi, everyone. Good morning. Hmm. Yes, so what was the last part that we have discussed? And do you guys have any questions in the last session? Hmm. Yes, guys. Do you have any questions in the last session? In the last session, we have started with disadvantages of decision trees. In the last session, we have started with disadvantages of decision trees. And we have seen that first and very most common example of disadvantages of decision trees are it overfits the data. Second is it is unstable. A few changes in the data can considerably change a decision tree, right? Then, um, then you have seen the most informative feature are always towards the top of the tree, right? Always towards the top of a tree. Now, um, we will discuss the next part, that is tree truncation. Let us discuss this and then we'll start with the next part. Yeah, truncation and pruning is the next thing that we are going to discuss. Then we'll start with the coding part, that is hyperparameter tuning, and then we'll see decision tree regression. So for today's session, this is only going to be theoretical part and it will be wholesome coding, right? This is also very important part, tree tree truncation. So earlier you learned that decision trees have a strong tendency to overfit the data, right? Which is a serious problem. So you need to pay attention to the size of the tree. You always need to pay attention to the size of the tree. Yes or no? A large tree will have a leaf only to cater a single data point. A large tree will have a leaf only to cater a single data point. And there are two broad categories or strategies to control overfitting, right? So we are discussing the tools or the techniques that we have to control the overfitting problem. So there are two widely used measure. One is truncation, and second one is pruning. One is truncation, and second one is pruning. So we'll discuss these two methods one by one now. So what happens is, first of all, let us discuss the truncation. What is that? We stop the tree while it is still growing so that it not end up may not end up with leaves containing very few data points, right? We stop the tree while it is growing so that it may not end up with the leaves containing very few data points. And this is also known as pre-pruning. It means that we are stopping the tree before actually it grows, right? So suppose this is just a minute. Just give me a minute, guys. Yes. So suppose this is your tree. It is growing. While growing itself, you found that uh, at this particular leaf node, we have very few data points. Let's say only one or two data points. So it means just a minute. Just give me a minute. So while growing the tree itself, uh, you found that at this particular leaf node, we have only few data points. So it is not necessary. So you directly prune that. You cut that branch, right? This happens at the back end. You guys don't be actually doing this, but this is something which is very helpful, which will solve your problem of overfitting, which is nothing but training accuracy will be very good, but your testing accuracy will be poor. So that is the one thing that we have to reduce the overfitting problem. That is known as truncation, right? It means while growing the tree itself, you observe this, your model will observe this and it will cut. This is also known as pre-pruning, right? Pre-pruning. But on the other hand, you have pruning technique where you let the tree grows till the last point. You let this tree grow to the last point, and then after once the tree grows fully, once it is fully developed, then you check and you observe that this is not giving me the correct idea, or this is not the correct representation of the homogeneity, or this particular node has very less reduction in the impurity, right? So it is not necessary, it is redundant, it is not making any effect on the prediction or the decision. So you cut that. You cut this once the tree is built perfectly fine, completely, right? Once this tree is built completely, right? So that's what we have. Yes or no? So truncation means we stop the tree while it's still growing, and pruning means let the tree grow to any complexity, and then you cut the branches of the tree in a bottom up fashion, starting from the leaves. And it is more common to use pruning strategies to avoid overfitting in practical implementation, right? So practically we are going to use pruning technique only once the tree grows fully. We um, cut that. This is practically used We don't use truncation. And please note that this entire thing or this entire session, we are going to cover mainly the truncation techniques. In case you want to learn more about pruning, I'll give you some resources which is completely independent. We have provided, I'll provide some links or materials that you guys can refer, right? So the truncation is something which I personally like or which we use in the industry as well. But pruning is also possible and you guys can also do that, right? Now, um, this pruning is something which you guys can, I obviously I'm going to provide some links to this. You can go and read about that, research about that. But that is something which you should go uh, once we complete the hyperparameter tuning part. So you should get an idea about the hyperparameter tuning, and then it will be very easy for you to just have a look at the pruning technique, right? Now let us look at the various ways you can truncate the tree, right? Let's look at various ways in which you can truncate the or truncate a tree, basically. So it's very simple, actually. You guys can also easily think of ways, various ways in which you can truncate the tree. It's very simple. Most of you guys already have uh, uh, have had a thought on how we should do the truncation. First is we have to the minimum size, limit the minimum size of a partition after a split, right? For an example, let's say if I have done splitting at this node itself, I have enough amount of data. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 data are there. But at this node itself, suppose you do the splitting again, and at this node itself, you have only 1, 2, 3. So we say that here we have enough samples for splitting. We have enough samples for splitting. But at this node, we don't have enough sample. We don't have not enough samples. So we do not split. We do not split, right? So that is something which is this particular point, that is limit the minimum size of a partition after a split. Then we have minimum change, minimum change, minimum change in the measure of homogeneity. Minimum change in the measure of homogeneity. Very simple. Third is, for an example, minimum change in the measure of homogeneity means you are calculating the Gini index, yes or no? Reduction in the homogeneity or changing in the uh, impurity of the data. So you set a threshold, like if you do a splitting for, let's say, if you remember the example we had motivation and energy for the gym, right? And let's say if you do splitting based on the motivation, the reduction in the entropy, that is information gain, is let's say 0.05, right? And if you do splitting based on the energy, based on the energy for the person to go in a gym, the reduction in the gain is 0.15. Or reduction, sorry, gain in the impurity is your 0.15. So you set a threshold that minimum change in the measure of homogeneity should be at least 0.15 or greater than that. So obviously this will discard this particular feature, that is motivation, because It gives you information gain of only 0.05. So you set a threshold of 0.15, let's say, and you only accept that, right? So 0.15 greater than or equals to 0.15. This is just an example, not necessary we should consider this only. So minimum change in the measure of n homogeneity should be 0.15 only. If it is achieved, I'll stop the splitting criteria. I'll not be splitting furthermore. And you guys can uh, you guys can be able to resolve your problem of your overfitting. Yes or no? Then we have to limit the depth of the tree. For an example, we suppose we are splitting our tree like this, right? So we set limit of only 4 levels, right? Sample, it is known as depth basically. We'll come to that point after 5 minutes. So only 4 levels, only 4 levels. So 1, 2, 3, and 4. Beyond that, I don't want any splitting, even if it is possible, right? So unnecessarily overfitting will be stopped, and you guys can limit the depth of the tree. That is your third method to method of truncation, right? Fourth could be you have to set a minimum threshold on the number of samples that appear in a leaf. You have to set a minimum threshold on the number of samples that appear in a leaf, right? So minimum threshold of number of sample appear in a leaf. So if you do splitting, let's say this is your data, again you do splitting, further it is not possible. So suppose this is your leaf node. This is your leaf node where further splitting is not possible, right? So you set a minimum threshold of number of samples that leaf should carry. Let's say this has 5. We are setting minimum sample leaf. There is one parameter, minimum sample leaf. If you go to official documentation of decision tree, you'll be able to understand that. Anyway, that is something which we are going to discuss now. So max depth is something, it is related to this, the limit of the depth of the tree, that is max depth. You control that. Then minimum sample split is something here, first point, that is minimum size of a partition after split. And minimum sample leaf, that is minimum number of samples requires to be at a leaf node. That is something which you control, right? So you pass these parameters so that it will be automatically controlled, right? So to just give you guys a disclaimer, we are controlling this manually. Yes or no? Manually, I'm writing down minimum sample. What was that? Minimum sample split. Yeah. Manually, we are writing this down, right? We don't have any control automatically. We have to specify this manually, and then it will be taken care of, right? This is max depth. Yes or no? And this is minimum samples leave. The reason why I'm stating this point, manual control, because we are going to see one more thing where there's automatic control. You don't have to control, uh, you don't have to put this manually. There is automatic thing, which also we are going to study in today's session. That's the reason I have given much focus on this point, that this is a manual approach. This is your manual approach. So you set a minimum threshold on a number of samples that appear in a leaf, right? So this particular leaf should contain 4 data points or 5 data points. And last but not the least, you have to set a limit on the maximum number of leaves present in the tree. So there should be only 5 leaf node or 4 leaf nodes. So minimum weight fraction leaf, I think, no, maximum leaf node. Yeah, this one. So you pass this parameter, right? Maximum leaf nodes, you pass this parameter and it will be taken care. So these are the 5 different approaches which you set to do the truncation. As simple as that. So though there are various ways to truncate or prune trees, as you can see, we have different parameters like splitter, criterion, you can always go to decision tree classifier, official documentation, and explore these parameters, right? You can go to this and explore this, uh, which provides us the following hyperparameters which you can control. So I'll just discuss some of the parameters over here to just give you guys an basic idea about these parameters. So what is criterion first? The function is used to measure the quality of a split, that is support a criteria or Gini for the Gini impurity or log loss or the entropy. So which criterion you are selecting to further divide the tree. So it defines the homogeneity metric to measure the quality of the split. In the last session itself, we have discussed homogeneity measures are classification error, Gini index, right? And what was the other? We have seen three: Gini index, and last but not the least was entropy, right? So which one we should select? Either it should be log loss or entropy or Gini, right? So that is what we have. Second is max features. It is nothing but it defines the number of features to consider when looking for the best split. So we can put any integer value, any string value, any float value in this, right? Then we have max depth. We have discussed this point. What is max depth? It is the depth denotes the maximum depth of the tree. Maximum depth of a tree, and it can take any integer value or none. If none, then nodes are expanded until, if you pass this none, means if you don't pass any parameters, the nodes are expanded are expanded until all leaves contain just one data point, just one data point, and it leads to overfitting. Obviously, what it will do is it will leads to overfitting. That's the reason your model gets overfitted. That is what we have. Then further you can have minimum samples split and minimum sample leaf. That is what we have. So there are other hyperparameters as well. If you just go to this, you'll you can read that. And also we are going to use this in our hyperparameter tuning, right? So this is what we have for this entire thing. Now what I'll do is I'll share one file on your drive, and we are going to actually work on the building a decision tree model by using hyperparameter tuning, right? So today I think it's day 27, right? Day 27, 5th Jan 5 decision tree. Random forest also we are going to discuss in today's session, and we are going to discuss hyperparameter tuning, right? All right. So let me add that file. Everyone has that particular data set, which is heart disease, heart V2, heart underscore V2, this one, right? And I'll just create a new collab notebook, create and share. If you want to do simultaneously this with me, you can do, but today we are going to just go little bit fast, right? We still have to cover one more machine learning model in today's session, right? So let me just put the heading as hyperparameter tuning. decision tree, right? So I'll go to directly to, ठीक है. I'll go to, first of all, we'll just load that data. We'll just go to that data. We'll just load that data. But wait to see. Yeah. It is loaded. Now let us we are going to work on two problem statement here. So there will be two data sets on which we are going to perform the decision tree model, right? So very first thing is we import the necessary libraries, right? We'll import pandas as pd, we'll import numpy as np, we'll import cborn as sns, and we'll write on matplotlib dot pyplot as plt, right? Then we'll read the CSV file and put it into df object. We'll write on df is equals to pd.read underscore CSV, and we'll just take out this thing, copy path, paste it over. And we'll write on df.columns, then df.head, right? As I already have told, decision tree does not require treatment of the outliers because it is not sensitive to outliers, right? It is non-parametric model. So we directly will jump to this part, that is putting the feature variable to x, that is capital X equals to df dot drop. We are going to drop heart disease, comma, axis is equals to 1, right? And we are going to put response variable to y, right? And y is equals to df dot heart disease, right? Then we'll return from sklearn dot model underscore selection. We're going to import train underscore test underscore split. And then there will be train test split x train underscore x underscore test, comma, y underscore train, comma, y underscore test is equals to the package name train test split. And you guys are already familiar with this, so I'll not be explaining this how to do the train test split. Random state, any random state value, and just check x train dot shape, comma, x underscore test dot shape, right? Now we are going to fit the decision tree with default parameters, which is 3 decision tree classifier. Let's fit the default parameter of max depth. So any parameters you can pass. And yeah, so what was this? Yes, we are going to fit a decision tree, fitting the decision tree with default hyperparameters apart from max underscore depth, which is 3, so that we can plot and read the tree. From sklearn dot tree, we are going to import decision tree classifier, and we'll return dt is equals to decision tree. Decision tree classifier. Spelling is wrong. Decision tree classifier. Yeah. And max depth equals to 3. Second is we fit the model on X and Y tray. So this is your model fitting steps. First step is object creation. You are going to create the object. Second step is model fitting. So you fit the model. And here we will require to install the we'll require to install the GraphViz, but that is something which I will not be doing right now. So I told you guys, we already have seen another method to directly visualize the tree, right? So let me check that first of all. We'll directly be using that to visualize the tree. We'll not be installing the um, GraphViz package, right? Just a minute. It's the yeah. Alternatives we have from sklearn.tree. We're going to import plot underscore tree first, and we'll write down pld.figure. Figure size you can set as any size, let's say 60, 30. From this plot underscore tree, we'll write down dt, comma, feature underscore names is equals to x dot columns, comma, class underscore names is equals to no disease, comma, disease, right? And we'll write down field is equals to true. Let us run this. Field is not defined. We need to import package, import matplotlib dot pyplot as plt. Then run this. Not be an integer. plt.figure. Okay, fix size is missing. Is equals to this 60, 30. Anything more? Yeah. So this is your decision tree for max depth equals to 3. This is 1, this is 2, and this is 3, right? You can get the same output by using GraphViz, but that is not something which we should use. Okay, now we will evaluate the model performance. We'll evaluate the model performance. We'll write on y underscore train underscore pred is equals to dt dot predict xtrain, and y underscore test underscore pred is equals to dt dot predict x underscore test, right? Then from sklearn dot metrics, I'm going to import confusion matrix, comma, accuracy score, right? Then I'm going to print accuracy score of y underscore train, comma, y underscore test underscore pred, right? Then confusion matrix, confusion matrix, y underscore train, y underscore train underscore pred, right? So my accuracy is, this should be y train pred, right? My accuracy is 74.74% on the test on the train data set. And let us do the same thing. Let us do the same thing on test. The y test. Here this should be y test. Right? And this one also should be y test. This one should be y test. Right? So that is what we have over here. So my accuracy is for testing set is 0.60, that is 60%. And this model is obviously doing the overfitting. Now, instead of this, what I'll do is I'll let this decision tree grow till the time um, it achieves the final splitting, right? So we are not setting any of max depth is equals to 3 as we have done over here, right? We are not allowing, we are not putting any restriction. We are freely allowing that particular decision tree to grow and get us the output. So even though at this point itself, we have a notion that it will obviously be overfitting because this is default decision tree. We are not putting any restriction to that, but we are just interested to check what will be the output or how this um, tree will grow, right? Randomly. So instead of dt, we'll use dt underscore default. That's it. And apart from that, everything will be simple. Yeah. So as you can see in dt default, we are not putting any max depth, minimum sample leaf, maximum sample leaf. We are not putting anything. And directly you can see it is very, can you see this? We are allowing our decision tree to grow fully. And as it is very greedy, so it is doing the split. And um, for this, if you want to evaluate the performance, it is always and always will be overfitting that your decision tree will give you 100% training accuracy, 100% training. And 100% training accuracy means your um, model is overfitted. I'll explain that. So let us try to find the training and testing accuracy over here, right? So for that, I will create a helper function. In that, we are going to pass dt underscore default. Perfect. So let us create that function, evaluate model. In that, I'm interested to pass only and only the model. Which model, whatever model or whichever model we are using, we'll pass that. I'm going to print train accuracy will be accuracy score between my y train and dt classifier dot predict x train. Perfect. Print train confusion matrix will be confusion matrix y train dt underscore classifier dot predict x train, right? Then print uh, we can do this one into 50. So 50 times hyphen will be there. Then we'll just print test accuracy. Test accuracy will be exactly equals to accuracy underscore between y underscore test, comma dt underscore classifier dot predict x test. We'll do the confusion matrix over here. Yes, for test, right? Now it is created. It's time to use this. I want to use what? This function evaluate model. In that you need to pass the classifier. So we have rename or we have put a name. Okay, I don't want this. So what should we do? We should use plt.show, right? Description about the graph will be removed by plt.show, right? So we'll use this dt underscore default parameter, and we'll be actually calling that function of evaluate model, right? Let us do that, and let's find the training accuracy is 100% and testing accuracy is 62. What is this notion of training accuracy 100%? What do you think, guys? It just like it just like um, the fact that, let's say you have NEET exam, you might be familiar with this fraud, right? Which has happened recently. I think 6 students from a particular center in Noida or Delhi. I'm not sure about this, but the 6 students, they have got 720 out of 720 marks, right? From the same center itself. So they have investigated this particular scenario, and they found that there is there was a fraud of paper leak, right? So this is something similar to this particular example, right? You have shown everything to your model. Everything means there is no any test set. You have shown everything. So obviously your model knows all the pattern, all the data points, and you're asking your model to predict that, right? So it will give 100% accuracy. It's same like you're showing everything, every data point to the model in the training set, every data point in the model in the training set, and it will give you 100% accuracy, right? Right. And if you are asking to predict that, so it will predict at first position we have this point, second position at this point, third position we have this point. It's same like you have a question paper before the exam itself, right? You have same question paper consisting of 50 questions, and the same paper you got before the day of exam itself. And on the day of exam, you are able to solve everything itself because you had question as well as answers, right? So that is what the problem is. If you let your decision tree grows itself, it will grow very randomly, and it will give you 100% training accuracy, right? But testing accuracy is very poor. So if the training accuracy is 100%, the other case would be your model is so perfectly trained. Your model is so perfectly trained that it is able to predict each and every pattern from the data. And the case should be testing accuracy should also should be high if the training is good, right? It is same like asking those 6 students who have appeared in the exam. um, they you might have read that news that retake was happened, retake of that particular exam, and this 6 student, out of this only 3 or 2 student got the 705 or something like that, right? So they came to the conclusion that paper was leak. So that should not be the case, right? That should not be the case. Okay. So that is what we have. Just give me a minute. There's a power cut over here. And because of, just give me a minute, guys. Till the time you go through this, Yeah. All right. So that's the reason we should not let our decision tree grow fully by its own, right? So that is what we have for this particular thing. Now we should go to the next part, that is controlling the depth of the tree, right? Controlling, I want to control the depth of the tree now. Controlling the depth of the tree. And suppose if you are very naive, you don't have any idea about the decision tree, you can directly seek for the help by just writing down this question mark decision tree classifier. It means that you want help regarding this particular package of decision tree classifier. So it will give you everything related to this official documentation. Obviously, you can go and go check the official documentation, but you want the help itself in the IDE, Python IDE, or IDLE. You can always seek help from this, right? Now, what I'll do is I'll set a minimum depth. Let us do that. So decision tree classifier, decision tree classifier. I'm going to write on max depth, set a max depth, which should be exactly equals to, just a minute. Anything you can pass. Let me pass 5 and random state. I'll pass this. Now there will be um yeah, max depth is equals to 3 or 5. Let us go with the 5. And again, let us plot the decision tree by using this same thing, where instead of dt underscore default, what should be there now? It should be dt underscore depth. dt underscore depth. As simple as that. And uh, you will call this evaluate model function on which decision tree? It will be dt underscore depth, obviously. dt underscore depth. Simple. Now, if you see, it is 85%, right? Because we have controlled the depth of the tree, right? Now it is good. Then we can specify the minimum sample leaf, right? Specifying the minimum samples before splitting. So this time it will be decision tree and underscore minimum underscore split. And in that, we'll call the package decision tree classifier. And that will pass minimum sample split. Let us put as 10, right? You can pass anything. I'll just pass 10. Let me pass 20 or 15. Anything is fine. Don't worry. I'll just select this and I am going to pass this. Instead of this, it should be dt underscore minimum underscore split. Simple. And we'll call the evaluate model function again. In that, we'll pass decision tree underscore minimum underscore split over here. So now it is 83. So if you observe one thing, we are reducing the difference between the accuracy between your training and testing subset, right? The difference should be as low as possible. Ideally, it should be in between 5. I mean, less than or equals to 5. The difference between training accuracy and testing accuracy. If it is less than or equals to 5, it it means that it means that your decision tree is not overfitted or your model is not overfitted. So ideally, the difference should be less than or equals to 5. So likewise, to specify the minimum samples in leaf node, minimum samples in leaf node. So I'll write on entry underscore minimum underscore leaf is equals to the entry classifier. In that, we'll pass minimum underscore samples underscore leaf is equals to, let's go with the 20 here, x trend, y trend, right? And it's time to again visualize this and call the evaluate model part. Here it should be minimum leaf, right? And evaluate model should be there. Evaluate model should be there. Minimum leaf. Now it is 70 minus 64. It is somewhere around 6%, right? Now you can use the criterion is equals to entropy. So using criterion is equals to entropy. So you'll write down decision tree underscore minimum underscore leaf underscore entropy. You found that leaf is the correct parameter that we should use in order to reduce the overfitting. So we'll pass minimum sample leaf is equals to this, criterion is equals to 20, yes, and fit this. And then we'll visualize this model again. We'll visualize this model again here, right? And there will be again evaluate model part, which should be here. Right? It should be here. Then instead of entropy, we should go with the Gini now. So we can put a heading as using criterion is equals to Gini. Right? So if you go to this official documentation, here we are using Gini over there. So I'm going to write down Gini, 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 or Gini. Right? It should be, just a minute. Minimum leaf, instead of that, it should be minimum leaf underscore entropy, right? That's the reason. And here also minimum leaf underscore entropy. Yeah, nothing is changed. Okay, no problem. So here it should be minimum underscore leaf underscore Gini now. And here also it should be Gini now. Right? Perfect. Now we will visualize our data. Visualize our data on this part. It should be Gini instead of entropy. It should be Gini. And we'll call this evaluate model function that we have created on the Gini part. Right? So likewise, you can do, but as you have seen, this is manual, right? Isn't it manual approach? Always adding these parameters by our own. Isn't it manual? So instead of that, we have automatic approach where we have grid search CV and we have random search CV. We'll make use of that concept in order to search the parameter, search the best parameter out of this, all the parameters that we can pass, right? So it's very interesting We will use grid search CV, but I'll explain both the topic. So I'll just call a package from sklearn dot model underscore selection. I'm going to import grid search CV. So I can write down over here grid search CV package. Right, I can write down this over here. That is my package. This is my grid search CV package. So I'll just write down over here, right? And how to do the hyperparameter tuning, that should be our heading now for this, but that is something which we will study after the break. So let's have a break. Hyperparameter tuning, or we can do this, no problem. Yeah, hyperparameter tuning, right? So let's do that. Let's do that. Decision tree classifier. In that, we'll only pass random state. That's all. Will not pass anything because we are going to create a parameter list, parameter dictionary. In that, we are going to pass each and every parameter one by one. So I'll pass max depth. Ideally, max depth should be any integer value. So I would be creating a parameter list, and any parameter you can pass. Not necessary you can pass this parameter only, but this is just an example. Then I'll select minimum sample leaf. Again, it should be 5, 10, 50, 100, any parameter, and minimum sample split, anything. Just remember, if you just pass a list of n number of parameters, let's say here I have passed only 5, right? We only have passed 5 parameters. You can pass parameters wherein you can have 20 to 30 parameters. But the more the parameters, more time it should take to get the output. So the computation time will be very high, right? Your normal system means your laptop, your computer, will not be useful at this point where you are passing, let's say, all the parameters out there, all the parameters from this to this, and you're passing all the 20 to 30 parameters out there. Means instead of this 5, there will be 20 to 30 parameters um, in this list, right? At this time, you try to do that. Obviously, you'll get the result, but there might be chance that you will require 2 hours straight, or 3 hours, or 4 hours. Might be days, one day, something like that. This is because it requires high computational time and memory and space. So your normal system will not be capable to do that. You have to buy the resources. Um, you have to buy the GPU over here. So free GPUs are only this T4. Here we are using CPU, but there's one more thing which is available for free. I think it is for 10 times or something like that. 10 hours, only 10 hours of GPUs are available, but you can obviously go and purchase the additional compute units if you are interested to do that. So your Google, this collab will offer you different GPUs which are high, uh, which are capable to process the high uh, or advanced part, right? So that's the reason you might have seen this news that NVIDIA is, excuse me, excuse me. So NVIDIA, basically, they have, I mean, they from nowhere they are into trend, and their stock price is increasing because of the fact that these large language models or highly advanced models, they require high GPU or advanced GPU, right? So this this company provides the processing units. You might have seen this guy on the India tour, right? And having a chat with Ambani, right? Are you familiar with this news, guys? So basically, he's a CEO of this organization, and he recently came to India to discuss the future opportunities of AI associated with Reliance, right? So nowadays, it's very, I mean, not only for gaming. Earlier, this organization was solely and wholly focused on, they were focusing on gaming graphic processing unit or CPU. But nowadays, this task, the advanced model, they require to have advanced GPU, right? So that's the reason this company is in boom nowadays. All right. So what we were discussing now is we are discussing this point that here, as we are doing in the local system itself, it is not capable to uh, go beyond certain limit. So we'll not give much stress to our processing unit, right? Criterion last parameter will pass as Gini and entropy. So you can pass that entropy. And I'll just close this. Now it's time to use, maybe you mean, okay, it should not be is equals to, it should be colon. Yeah, it should be colon always. Remember this. Because if you see official documentation here also, they have used colon, right? All right. So if I just run this, I'll be getting the output. And now it's time to go for grid search. What is that? Grid search. We will discuss this now versus random search. CV. All right. So if you just see a visual representation of grid search CV versus random search CV, right? It is exactly like this, guys. Or is it is exactly like this one, right? You pass a grid of parameters, right? You pass a grid of parameters, as you can see in this uh, here itself. Let's take let's take only max depth, right? Suppose this is a grid of max depth. This is a grid of max depth. All right. So let's do this. Ideally, it should be maximum parameters, but we are passing only 5. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? So we're passing these parameters. Let's say we have passed 20 parameters instead of 5, right? What this grid search CV will do, it will search grid by grid. It will search at this grid. It will find accuracy at this grid. Means max depth, it will take initially is equals to 1. Let's say this is 1, 2. Let's call this as 1, 2, 3, 4, 5. Likewise, we have 20. So instead of this 2, 3, 5, 10, 20, let's imagine you have a max depth is equals to 1, 2, 3 up to 20, right? So 20 parameters are there. So it will take max depth equals to 1, like we have discussed, or we have taken this thing, right? Max depth is equals to above we have, yeah, max depth equals to 5 we have taken, no, and we have calculated the accuracy. For 5 we are getting 85. So similarly, For max depth equals to 1, max depth is equals to 1, we'll get some accuracy. We'll get some accuracy. For max depth is equals to 2, you'll get some accuracy. Yes or no? For max depth equals to 3, you'll get some accuracy. For max depth equals to 4, you'll get some accuracy. So similarly, you'll get 20 accuracies like this. And after performing the 20 accuracy, you can easily compare that. Let's say for max depth equals to 7, max depth equals to 7, you guys are getting the high accuracy, maximum accuracy, and you'll select that particular thing. So it is as simple as this, like you are searching the accuracy for each parameter grade by grade, right? That's why it is called as grid search CV. That's why it is called as grid search CV. On the other hand, random search CV, what it does is randomly it will select any parameters out there. It will find parameters over here. It will find accuracy, let's say over here, then here, then here, then here, then here, then here, then here. Like randomly, not line by line. 1, 2, 3, 4, 5, 6, this, not line by line. So that's the reason the name is random search. The search will happen randomly. 1, 2, 3, 4, 5, 6, 7. And if it will compare this 7 iteration itself, and in this 7 iteration, it will get the maximum accuracy, right? And it will take that. So there are certain advantages and disadvantages of random search and grid search. Um, Let us write down that one by one so that you can have a copy of this. So random search versus grid search. See, we'll discuss this first. Let us discuss this first. Okay, so random search will be requiring less time as compared to grid search. Yes or no? Because grid search does grid by grid approach. So less time, high time. And there are certain advantages and disadvantages that you can obviously read from any blogs out there. Any blog you can take. So in terms of performance, there is no clear winner between random search and grid search. It depends on the specific problem and the hyperparameter space. Random search is generally more efficient when the hyperparameter space is large and the optimal hyperparameters are not highly correlated. Whereas grid search is more efficient when the parameters are highly correlated and have strong interaction effect. So both are widely used. You can also explore this documentation where you'll find the difference between them. We define a search space using this, pass this. Okay, not this. Search is entire space by trying all the possible combination. Grid search will search the entire space by trying all the possible combinations of hyperparameters, and this can be very computationally expensive, especially if the search is large and if the model takes a long time to fit. However, it is guaranteed to find the optimal set of hyperparameters if it is able to complete the search, right? So another thing is this is guaranteed. It is guaranteed to find the optimal parameter. And this is just hypothetical, like there is no guarantee we can say to get the optimal solution, right? But for time being, if the time is very less and if you don't require high computational space and time, you should go with random search. So there's no any problem, totally fine. You can go with any parameters out there. This was just an example. And what about cross validation? That is also very, very important part, which we'll exclusively discuss after the break. So let's put this theoretical perspective point as the the topic that should we should discuss after the break, right? Now, what is left for us is we should um, do the hyperparameter tuning first. Hyperparameter tuning we should go with. So grid search CV, yeah, we have imported the package for grid search CV. We will be going with the grid search CV now, right? So what we'll do is we'll write on grid search CV an object, or grid search is also fine. Grid underscore search is equals to grid search CV. In that we'll pass is equals to estimator is equals to this decision tree dt. Estimator means nothing but it is nothing but your model that you are using. We have another parameter, that is param is equals to param underscore grid. Actually, you can see over here param grid, right? So grid cell CV, if you go to official documentation of grid cell CV, you'll be able to understand what are the different parameters that we can pass. Anyway, if you write down question mark and grid cell CV, that is also totally allowed, which will you guys will get the help of this grid search CV and what are the different parameters you can pass. I'm using grid search CV. In that I'm passing estimator, I'm passing param grid. My param grid is the params that we have just selected. It is not necessary that you should select only this. You can explore more. Then CV is equals to 4. What is this? I'll explain. We'll discuss this exclusively. So at this point of time, we'll not discuss. And I am interested to pass some parameters which are redundant, not necessary to pass this, but just in order to make our model heavy, I'll be using that. This is not um, compulsory. You can pass different parameters, right? Then I'll be passing time to find the time required for this, and grid underscore search will be fitting this on x underscore train comma y underscore train, right? It will take time. You can see that we have 800 fits out there. So 800 iteration will be there. And then there will be score underscore df, which is exactly equals to this. pd.data frame will take a result from grid search CV and will convert that into data frame. So for each and every parameter out there, see, isn't it very easy? For each and every parameter, you are getting mean score time, standards time, parameter criterion, and parameter max depth, minimum sample leaf, and its performance, right? Its performance score, accuracy score for each and every parameters. So let's say if criterion is Gini, max depth is 2, minimum sample split is blah, blah, blah. You'll get this accuracy. So likewise, we had how much? We had 800 combination, right? Shape, if you just check, 200, sorry, it was 200. Like for suppose if you take max depth is equals to 2 and minimum sample 5, 2 Gini, this will be one combination. Another combination will be 2, 10, 5 Gini. Third combination will be 2, 20, 10 Gini, right? So likewise, there are 200 combinations, right? And just imagine if we could have passed 10 or 100 parameters or 20 parameters in a single max depth or minimum sample leaf, it would have been very, very highly computational, right? It should require a high computational time and space. Yes or no? And out of this, I'm interested to find only 5 largest. So there's one function called as n largest. I want 5 top uh, mean test score. So for the uh, top 5 test accuracy. I'm just passing this, right? So these are the top 5 records that you have. And there's one more thing that you have, which is grid underscore search underscore dot best underscore estimator, which will simply give you that if you pass underscore is missing. If you pass this list of parameter, this combination of parameter, like criterion should be entropy, max depth equals to 3, minimum sample leaf equals to 5, minimum sample split equals to 20, and random state equals to 42, you guys will be getting the maximum accuracy, right? Out of the all combination possible, you guys will be getting the maximum accuracy for this. So we'll create an object of dt underscore best. In that, we'll be passing this parameters only, and we'll find the accuracy. As simple as this. So you don't need to require to have a search to do the search manually. You will be directly fitting your model on these best parameters out there, 71 and 61. This is the best possible case scenario for your model out of the all scenarios out there, right? And you will write down from sklearn dot model underscore selection, or sorry, metrics. You'll be importing classification report, and you'll be actually uh, printing this classification report. You'll be doing that between y underscore test and dt underscore best dot predict and x underscore test, right? So that's your classification report, and that is what your model is. If you want to visualize the decision tree, like this for the best parameters out there, you can do, and that will be your last step for this. So instead of this, I'll be passing dt underscore best, right? dt underscore best. So that is my best decision tree out of all the combination which we have passed under the parameter grid. Right? This is my best decision tree out of the parameters that I specifically have passed, right? These parameters. Not necessarily this is universal uh, uh, best parameter. For this problem statement, for this data, we have this possible combination out there. Is it clear now, everyone? Do you guys have any questions till now, whatever we have discussed till now? Anybody? Any doubts? Yes, guys. Yes, Arvind, Arivoli, Chandramohan, Darshini, Gopi, Avantika, Karthik, Madhu, Maulya. We have Murli, Prasita, Sai, Sharmila, Sai Kiran, sorry, Sri Karan, Thammi, Varun, Karthik, and Venu. Anyone have any doubts, any questions till now? Yeah.
Sir,
Yes.
sir, we can compare the functionalities of the random search CV and the grid search CV, sir.
You can compare.
Can we compare the random search CV functionalities and grid search CV functionalities, sir?
Functionalities means what sense?
Means,
Okay, got it. You can do that, no? Instead of random search CV, instead of grid search CV, you can just use random search over here. That's all. Nothing different. For an example, here I have done grid search CV, right? You can call a package for random search CV. So instead of grid search CV, wherever you have grid search, you can pass the random search over there, right?
Okay, sir. Okay.
Sir, is it okay to compromise the efficiency of test and train accuracy just to reduce the gap between them? There was a scenario when you used uh, minimum leaves, I guess.
Hmm.
In that, we had 65% for the test accuracy, and when
Mhm.
you used some other thing in the next time, it dropped to 64%. So our goal is to increase the test accuracy too, right?
Yeah. So first, anyway, it's very, very good question. See, I'll tell you this. You should remember this for all the models out there. See, our very first goal is to increase the accuracy, right? Increase the accuracy of your of the test subset or test set. But there should be a balance between the bias and variance. Yes or no? What is bias? It's your training data or training set, error associated with training set. Variance is your error associated with test, right? So you should always be doing this thing of maintaining the balance between training and testing data set at the cost of accuracy, right? We have seen this graph. Do you remember this graph? Sorry, it was uh, it was only like this, right? This one and this one. The black one is for variance, and on the x-axis we have number of samples, that is complexity. On x-axis you have accuracy, right? So there is no ideally, not ideally, practically there will not be any point where you have both the accuracies high, isn't it? Do you agree with this point, everyone? Ideally, there won't be any point as such where your accuracy, both the accuracy will be high, right? You have to compromise some accuracy to get the balance between training and testing accuracy, where both the error should be minimum at this point, both the error will be minimum. And you are okay, you are completely okay with this point, right? Because if you take point number A, let's say this is error, right? Not accuracy. Anyway, error is inversely proportional to accuracy, so you can relate with that error and accuracy. This is error, right? So ideally, your model should have less possible error, right? But at this point, let's say, let's calculate this error. This is 80, right? This is 80, suppose. And this one is, let's say, 5. And this one, point C is, let's say, 10, right? So let us consider 3 points. Point number A, where your training error is very high, bias is your training error, and where testing error is very low. It means that your testing accuracy is very high, excellent at this point, but training accuracy is very low, right? Bias is very, very high. Means training accuracy is very, very low. So you cannot select this practically. If you go with point number B, let's say your training accuracy is very, very excellent. Let's say training accuracy is 95%, but testing accuracy is very bad because at this point B, your testing error, the variance is 80, right? So ideally, you should achieve this position where you are not getting the best training accuracy and best testing accuracy, but the difference between both of them should be as minimum as possible, right? So there might be chance that even though your goal is to increase the testing accuracy, correct? You are going in the correct direction, but suppose your maximum training accuracy is, let's say, 92 or 95%, and maximum testing accuracy is 95%, let's say. But ideally or practically, is it possible to achieve this both position at the simultaneous time? It's not possible. Same time. So what we do is we come with this point. We search this point C, where you are completely okay. You're completely okay, where you should get training accuracy as um, let's say 90%, or even less than that, 87, 88 is also fine. And testing accuracy is also somewhat closer to that, 85, 86, right? That is totally fine. And for this condition, you go and do some hyperparameter tuning. Or there are certain techniques which we are going to study now. Hyperparameter tuning is one of them. Cross validation is one of them. That is something which we are going to discuss after the break. So at this point, I want this point only because practically there is no uh, best possible case scenario where you can maintain balance between training and testing, and there will be problem of overfitting. So for this condition, for this point number C, only we are making or trying to increase the accuracy, right? So anyway, very, very excellent question. Now is it clear, everyone? Yes?
Yes, sir.
Yes, Prasida? Very good. So that's the whole possible case scenario, right? So that's why I told bias and variance is very, very important. You should explore that particular point, bias and variance trade-off. It's very important. You can go and watch any video regarding this, right? But I have explained this in very simple possible scenario, possible case, because you'll not find any article explaining what is bias in very simple words, what is variance in simple words, what is point C in simple words, right? So that is something which is not available in very simple words, right? They have used more technical words. So that's the reason I only keep focusing or pushing my students to focus on very simple word explanation, right? Because you should, in real life scenario also, you should follow Occam's razor principle. Whenever it is possible to explain it in simple words, you should go and explain that. Chalo, all right. Do you guys want to discuss anything more? Yes, everyone? Anything more you want to discuss? Okay, think on this. Let let us have a break. Think what can be the questions. You can frame your questions and we can discuss this after the break. So let's have break till 10:58. All right. So let us discuss this cross-validation theoretical point, right? So just give me a minute. Just a minute. Okay. So, yeah, I'll just share my screen. Perfect. This one. So that was your question. I'll just put this somewhere over here. Yeah. And we'll just discuss about the cross validation. So let us specifically keep five, not five, more than at least 10 minutes uh, um, 10 to 15 minutes we can discuss this particular point, and it's very important as well. So whenever we build any machine learning model, we feed it with initial data to train the model, and then we feed some unknown data to understand how the model performs well and generalize over unseen, right? Unseen data. If the model performs well on unseen data, it is consistent and is able to predict with good accuracy on wide range of input data, then the model is stable. But this is not the case always. Machine learning model are not always stable. We have to evaluate the stability of machine learning model. This is where cross validation comes into the picture. What is cross validation? Yes. Anybody have any doubt? So it's a technique. It's a technique uh, used to assess how well our machine learning models perform on unseen data, right? So according to Wikipedia, if you go to Wikipedia definition, cross-validation is the process of assessing how the results of statistical analysis will generalize to an independent data set. Just go to Wikipedia and just have a look at this definition. So it is process of analyzing how the result of statistical analysis will generalize to an independent data set, right? So we'll learn about the four methods of cross-validation. We'll learn about the four methods. So first of all, why do we need cross-validation? Why do we need cross-validation? Why do we need cross-validation? Very simple answer to this is, suppose you are building a machine learning model to solve problem, and you have trained a model on a given data set, and when you check the accuracy of the model on the training data, it is close to 95%, right? And does this mean your model has trained very well and it is the best model because of high accuracy on the training data? That is not the case, right? Because your model trains on the given data and it understands the data well, captures even the minute variation and generalize effectively over the given data. If you expose the model to a completely new and unseen data, it might not predict with the same accuracy. It might fail to generalize well on the new data. And this problem is called as overfitting. Sometimes the model does not train well on the training data set itself and is not able to find the patterns. In this case, it would not perform well on the test set as well, and that is known as underfitting. So you guys know what is underfitting, what is overfitting, what is cross validation is. So that's why to overcome the problem, of overfitting, we use a technique called as cross validation. Right? So cross validation is a resampling technique with a fundamental idea of splitting the dataset into two parts, that is training and testing. Right? Trained dataset is used to train the model, and unseen data that is used for the prediction of the model. The model performs well over the test data with the good accuracy. It means that model hasn't overfitted the training data and can be used for the prediction. Right? So there are four ways in which you can train the model. What are those four techniques? First one is hold out method. Hold out method. What is that? This is simplest evaluation method and is widely used in machine learning projects, which you guys already are familiar about. That is, we split our data into train and test. That is simple method to what we can say to use the cross validation, right? We already have seen this. Simply dividing your data into train and test. And the data split happens randomly. We cannot be sure which data ends up in the train and which data ends up in the test bucket. Do we have any control on this? Which data in the train and which data in the test? Do we have any control over this? We don't have any control. So this can lead to extremely high variance every time. And the split changes. If the split changes, accuracy will also change. There might be chance that, suppose this is your data and this is your test set, this is your train set. There might be chance that here there are some important points that should be a part of training set. If you provide this data to your model for just learning the pattern, you might increase your model might increase the accuracy, right? There might be chances that your model will increase accuracy significantly. But the reason that this point are kept in the test set, you cannot have any control over that. It is completely unseen to your model. We do not show this model. So your model will not use these data points, right, for training. Your model will not use this data point for training. Yes or no? So that is the problem over here. While training the data, is a validation set the same as my training data set or just a fraction of my training? Validation is something which is a part of your test data set, right? That is something which we already have discussed. The test set is further divided into two parts. First is validation, second is test, like that. And this is your training, right? That is not important. Don't worry about that. But you should only know that we have validation and test. There are two subset in your test data, but that is not a concern over here, right? What is our problem statement is, if you do the holdout method, there might be chance that you are missing out on some important point which are part of test set, right? So I'll not be writing down this because we have very less time left. You can go and watch this recording, try to create your own notes for this particular point, right? So there are some drawbacks of this method, obviously. And one of the major advantage I can say for this method is it is very computationally efficient. Computationally efficient. What do you mean by this? It means time is very less, right? Then computational space required very less because you are doing simple trend split, right? Then there is leave one out cross validation. leave one out cross validation. Suppose you have 5 data points. Let's say let's say this is your data. Here 1, 2, 3, 4, 5. Right? Again 1, 2, 3, 4, 5. So what happens is 1, 2, 3, 4, 5. What happens is, suppose you only have 5 data points. Simple case, just so you are in leave one out method. What you do is, in first iteration or first iteration, your last part is a part of test set. All the other will be part of training set. Then what you'll do is you'll change the subset of testing. Here this will be test, suppose, right? Then rest of the set will be test training. Then again, this subset will be test, right? And again, this will be the data. This will be test. Again, this will be your data, entire data. This first will be part of test. So here, don't you think we are solving this problem that important data is a part of second uh, important data which is missing out in the test set? The problem of that is taken care of, right? For an example, if I only consider this, my important data point is a part of test, right? I want to use that in training, no? So it is used. Suppose for this data set, for this data, for this subset, this is important part and it is missing. So it is taken care over here in training, right? So alternatively, each one is a part of test set. So we are in a position that we show all the data points iteratively. All the data point is a part of training sometime or the other, right? Each and every data point, not all the data point, each and every data point has got chance to be a part of training, right? To be a part of training. So don't you think your problem of that important data point missing out in the process of training is taken care of, right? That is what is, but this thing is computationally expensive, meaning that here we have only taken 5 data points, but in real case you have 200 data points. So this process should be completed. It should take 200 iteration at least. Yes or no? If you have 200 data points, then there will be 200 iteration, right? That is the problem over here. So model run n times to test every observation in the data, right? And our next method will tackle this problem only, which gives a good balance between bias and variance. Next method will give good balance between bias and variance. So what happens is, you are getting, for first iteration, let's say you are getting 90% accuracy. For second iteration, you are getting 92. Third, let's say 86. Fourth, let's say 85, and last, let's say 88. So even though uh, for this split, do we have any control? Do we have any control of changing the test set in leave one out, sorry, in hold or out method? Do we have any control to change the test set? We don't have any control. So the accuracy is constant. It is not changing, right? So there might be chance that if you put this first set in as a part of test set, if you put this first set as a part of your test set, you will increase the accuracy from 90 to, let's say, 95, right? As you can see over here, suppose last part is a test, so it is 92, but the moment you shifted this test set to the left hand side and fourth part you are considering into test set, you can see that there is increase in the accuracy, right? So for some combination or the other, you will find that there might be chance that you guys can increase the accuracy. So what you do is, for final outcome, for final accuracy, You will take average of this accuracies, right? Average of this all the accuracies out there, and it is 88.2, and which is good, right? Instead of 86 and 85, it is 88.2. Is anytime it is good, right? So that's what the uh, advantage of this leave one out cross validation is. Third is your third type is your another type, which is k-fold cross validation. Third is k-fold cross validation. It's also a problem of creating 200 subset, or let's say creating n subset for the n data points. So k-fold cross validation, how it helps you out is let's say you have 1, 2, 3, 4, 5, and in that 5 data points you have 5. So 5 for this, 5 for this, 5, 5, 5. So totally, you suppose you have 5, 5, 5, 5, 5. It makes 25 data points, right? Right, 25 data points. Suppose you have 25 data points. So what you do is, suppose this 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. These are the data points, right? So what you do is, you create a set. K is nothing but you create a set. Let's say k is equals to 5. Our k value is 5. So first 5 set will be a part of test set, and rest of the data points will be part of your training set, right? Then you do this thing for the second time, second iteration, second set will be part of test, and you will do it third time. Third time will be third subset will be part of test. You do this fourth time, fourth will be part of test. Yes or no? You do this fifth time, fifth will be part of test. Fifth will be part of test. Simple. 1, 2, 3, 4, 5. Right? So instead of doing this 25 times as the leave one out method, if you could have used leave one out for this 25, so there will be 25 iteration. We are reducing iteration to 25, from 25 to 5. Yes or no? Only 5 iteration, and all the data points are a part of test and train every other time out there. So you guys will be solving that problem of computationally expensive, but still you have to perform this n times, right? Yes or no? Or k times, to be more precise. K times, right? So still there is a problem of computationally expensive than the normal method, that is leave one out, sorry, hold out method, because hold out method only requires one iteration. Here it requires k iteration depending upon the subset that you have chosen. Yes or no? So that is the disadvantage, but there will be low variance and there will be intermediate bias, and you are significantly reducing the problem of overfitting over there, right? Now the best hero comes out into the picture that we should use, we use in the industry, that is known as stratified k-fold CV. And what is that? We do this stratified sampling. There's one term in your statistics which is known as stratified sampling. I'll just throw a light on this concept for 2 minutes, and then we'll be discussing this cross validation practically, right? So what do you mean by stratified sampling? Suppose, let's say you have cosmetic data products, you have data which contains reviews of cosmetic product used by both male and female, right? Used by both male and female. So when we perform random sampling, we split data into train and test, right? We might not represent the most of the male data in the training set, which could end up in the test data set. And there is a problem, right? When we train the model on sample training data, that is not the correct representation of the actual population. The model will not predict the test data with good accuracy. So that is where your stratified sampling comes into the picture, comes to the rescue. Here we split the data to represent the all class from the population. Let us consider you have 1,000 reviews. You'll understand this now. And out of this 1,000 reviews, 60% reviews are from female population. That is 600 reviews are my female reviews. 40% is male. 40% is male. So 400 will be reviews. 400 reviews for male population, right? Sorry, not 400. Yeah, 60% of 1,000 is, yes, correct. Now, I want to split this data. I want to split this data into a constant of 80-20 split, right? What do you mean by that? 80 will be train, 20 will be test. Right? So 80 train and 20 test. So meaning that 80% means 0.8 into 1,000, which is exactly equals to 800 will be part of training and 200 will be part of test. But we have to take this in such a way that 800 of 600 reviews, not 800, 80% of 600 reviews, that is 480 reviews, should be from male, and again 0.8 of 400 reviews should be from male. Sorry, this should be female. This should be female reviews, and there should be male reviews, which is a part of training, right? So if you make a sum of this, it is obviously 800, and you are maintaining the 60-40 ratios, which were there in original dataset. Yes or no? You are maintaining the 60-40 ratio over there. Similarly, 20% will be part of test. So basically 200, 0.2 of 600 will be 120 is a part of female, and 20% of male, that is 400, will be part of test. So total, if you do sum, again, it comes out to be 200. Yes or no? So the ratio is maintained, right? And the split ratio is also maintained, 80-20, right? That is what your stratified sampling is. So even though if you make k fold, there's no any chance of uh, changing this particular combination of data which were there originally. It is in the same ratio itself, right? For an example, I'll just draw a figure. For an example, if this is my original data, right? My male population of female was high, right? So female is this and male is this, right? This is your you have to maintain this ratio, 600 of 400. So even though if I make small subset of this data, let's say this is entire data, I'm making 5 subset, stratified k fold, no? So 1, 2, 3, 4, 5, let's say. 1, 2, 3, 4, 5. I will make a same thing. 1, 2, 1, 2. The combination will be same, right? Combination will be same. This is my round 1. So similarly, you have one, because you have made 5 subset, and out of this 5 subset, let's say your first subset is a part of test now. Then second time, the combination will be same, proportion will be same, right? Now this time your second subset is a part of test. Now it's third time. Third time. 1, 2, 3, 4, 5. Third time, third subset will be part of test. So likewise, each and every subset is taken care of, which is a part of training set. So we are not missing out any data points which is a part of test. And if that particular point is important point, we are not missing that. But we are also maintaining the same ratio over here. That is known as stratified sampling. Is this thing clear, guys? Now, do you have any questions till now? Stratified sampling. Yes or no, guys? Do you have any questions in this? I can see only one response. What about other guys? Yes, this is your figure. I'm just adding this over here, right? So this is exactly what stratified k-fold CV is. And it will create k-folds by preserving the percentage of sample for each class. Now you would be having a question that why we have taken k is equals to 5 or k is equals to 5, let's say. Why I am only always taking k is equals to 5? Why not the other number? So very good answer for this is, statistically correct answer for this is, either k is equals to 5 or k is equals to 10 are good because of the empirical evidence. It shows these values yield test error estimates with low bias and low variance. So it is practically found that theoretically or mathematically that k value should be 5 or 10 always, then only you'll get the good accuracy. So even though if you use k-fold cross-validation, k value is 5 and 10 are considered, or stratified k-fold is, even though if you are using stratified k-fold, k values should be 5 or 10 only, right? So that's what the another point is. So you should always remember this point. If somebody asks you in the interview why k values are 5 or 10 only, then you should tell this answer to the interviewer out there, right? Now, major disadvantage of this, as every method has a disadvantage and advantage of their own. So major disadvantage of this model is it must run from scratch k times and make it more computationally expensive than the first holdout method. But it is better than all the models out there, and you should use only stratified k-fold always. You should only use stratified k-fold always, right? I think you can consider that this particular method does not have any disadvantage. That is also totally fine, right? So I should will write down over here that stratified k-fold CV does, and it will create k-folds by preserving percentage of sample for each class, and this solves the problem of random sampling associated with fold out and k-fold methods. Right? So that's what the idea is. ठीक है, you go through this, then we'll start the practical implementation part. All right, so let us do uh, let us work on another problem statement over here quickly. So I'll just upload the data and we'll be starting our journey of um, random forest model, second model, or other machine learning model. So I think the data which we will require is this one only, housing CSV. I'll create new Colab notebook and I will be uploading the data over here, right? So let's do this. And please allow me to do this little fast because we are still left with so much. We are still left with multiple models, and ideally it should not be allowed, but I'm giving this as part of the extra case study, right? So I would be doing this fast, but it is your duty to go and revise this after, I mean, just watch the recording and revise this, right? So let's do this. We have a problem statement that is housing case study where ideally, okay, I think I should copy the problem statement over here to save our time. Just give me a minute. So the problem statement is consider a real estate company where they wanted to they have a data set containing prices of properties in Delhi region, and it wishes to use the data to optimize the sale price of the properties based on the important factors such as area, such as area, bedrooms, parking, etc. So especially the company wants to identify the variables that affecting the prices, that is area, number of bedrooms, number of rooms or bathrooms. They want to create a linear model that quantitatively relates the house prices with variables such as number of rooms, area, number of bathrooms, and to know the accuracy of the model, how well these variables can predict the price of a house. So ideally, this problem statement is related to multiple linear regression, but we deep down the line, we are going to explore the random forest model and decision tree model for this as well, so that you can always relate different models out there, right? Okay. So we can relate and check the performance and compare the performance of the different machine learning models simultaneously. So let us check this out. I'll just copy this and I'm going to paste it over here, right? And this should be good. Okay. So step one is to always read and understand the data, right? So we'll just read the data out there. Just a minute. I already have done this project, so I'll be only copying and pasting this so that you will get what we can say, you get a more model, you get more case studies in less amount of time. And anyway, this is something which we already have done earlier, right? These steps will not be new for you, don't worry. So step one is always we read and understand the data. So what I'll do is I'll just copy this. This is your step number one. Let us first import numpys and pandas. We suppress the warning. We check the data. That is what we have done. Then what do we do is we inspect various aspects of the housing data frame that we have with us. So I'll write down that, inspect this. We'll write down df.info. We'll write down df.shape. Here we have imported data as housing, so it should be housing.info and housing.shape, right? Housing.shape. Okay, now it's time to go and describe the data set that we have. Then we'll visualize the data properly by using matplotlib and cmon. So I'll be just writing down this, right? Using matplotlib and cmon. So I'll copy this. I'm going to paste it over here. And I'll copy this. I'm going to paste it over here. Right? We are going to visualize the numeric variables by using pair plot. So we are getting pair plot. Anyway, we already have done the steps. If you go and check earlier models out there, then we are visualizing the categorical variables. We are visualizing the categorical variables. So as you might have noticed that there are few categorical variables for us, and we have to visualize that by using the different subplots. So box plot is the correct tool to visualize the categorical variable. And do we have any outliers or not? We have outliers, we have to remove that, right? So we can always visualize, we can also visualize some of these categorical variables parallelly by using HUE argument, right? So I'll be doing this. I'll be taking this thing over here, right? Then I'm going to prepare a data here. So I'll be writing down the steps of data preparation. You can see that your dataset has columns with values yes or no. But in order to fit a regression line, we would need numerical values, not a string values. And hence we need to convert them to ones and zeros, where one is yes and zero is no. So this is encoding, right? We'll do that quickly. We'll do that. And once the encoding is done, we'll check the housing data frame here, right? And then we'll create a dummy variables for some of the columns where there are multiple more than two entries for some of the columns out there. So we have three levels for some of the columns. That's the reason we should go with the encoding, one hot encoding or dummy variable. We'll do that, right? Then you don't need the three columns out there. The reason is dummy variable trap. So what you do is, for that, you would be dropping the first column out there by using drop underscore first is equals to 2, right? Now we'll drop the furnishing status over here. And then it's time to split the data into train and test. So we'll be writing down this, splitting data into train and test, and we'll require to work on this, importing the package. We'll rescale the data out there. We'll rescale the data. So we'll use min max scaling for that. And we'll use standardization as well. We'll be using min max scaling. We'll be using standardization for that. So you can go and do standardization. I generally prefer, or you can also prefer min max scaling in order to have all the data in a single range. Then we'll do describe for this data, right? Then we'll go with the heat map to check the multi-collinearity in the data out there. Then you might have noticed the area. It seems to be correlated with the price. So let us see a pair plot for the area versus price. Right? Now we'll divide your data into X and Y. What do you have in X? You have all the independent variables. What do you have in Y? You have target variable. So dividing your data into X and Y, then step 5 is building a linear model. Price. Is it capital P? No. Don't we have price column in X underscore train? We have price, no? What is happening for that? We have price. Okay, df underscore train. Is it? What is happening over here then? It says price. Unexpected argument access. Okay. Instead of pop, I'll write and drop. That should be equals to this, right? And y train will be only df of train of price, right? Let's see if it is happening or not. Price is not found in the axis. How come? Df underscore train. Don't we have price? Area is there. Okay. It's not there. Hmm. Df underscore train dot describe. We have price, no? Here also we have price. I'll just do restart and run on. Let's see this. Then we'll build the model. Then we are going to build the model. We'll build the model. So for that, we'll import stats model. We'll be using stats model library to just build the model. Even though it's not necessary, you can directly use sklearn. Right now it is done, correct. We'll use sklearn, that is also allowed. lr underscore params and visualize the scatter plot. This is something which we have done in your um, multiple linear regression model, right? So it should be the case. All right. Now we will be taking out the summary of this model. Then we'll add another variable and we'll build the multiple linear regression. This was simple linear regression. We'll be building multiple linear regression, right? So I'll just import this, adding another variable and checking the summary of this model. If we consider two variable, your R2 score increases, right? We have seen this in multiple linear regression. Then this is your conclusion for summary part. The conclusion is this. You can read that. Then I think we'll add another three variables we can add and find the model. So likewise, this is manual recursive feature selection, right? To check, to add every column out there at each iteration and check the increase or increment in the R2 score or the accuracy, right? Now we will be actually skipping this part and directly we still have VIF, right? We have to drop the variables and do that thing. I'll be posting this notebook. Our main agenda over here is to go with uh, decision tree model, right? So I'll be putting this heading as decision tree model. Right, I'll be doing this. And then I will be doing this. Then this thing. And we'll be fitting the decision tree model. And we can visualize the tree by using that from sklearn.tree, right? Then once this is done, we'll be using the R2 score and this everything to predict the performance of the model out there. R2 score is not important. Okay. From sklearn.metrics, that is remaining then. From sklearn.metrics, we'll import R2 score. Then we'll print R to score over here. And here also we'll print R to score here. Then we'll use random forest. Now it's time to use the random forest, which is our which was our agenda to discuss. Now we'll be using plain vanilla random forest machine learning model, and we'll be having a look at its performance, right? Performance in sense you'll be having a look at the model accuracy, right? So I will be doing this, and I will find the feature importance. This one. I'll be printing this, print R to score. I'll be printing this R to score for this. Okay. And I'll print this RF underscore feature importance. This one. Right. And I'll be creating a data frame where we'll get for each and every variable out there, we'll get the feature importance. Right. Yeah. So if you use your random forest, your R2 score and accuracies, sorry, R2 score for training is 67 and R2 score for testing is 58. And if you are using the decision tree, it is 62 and 52, right? So I'll just write down over here, decision tree, 62, train, test, 52 or 53, let's say. For random forest, RF, what was the case? It is 67, right? It is increased to 67.8, and this is increased to 58. So don't you think random forest, a plain vanilla random forest is better than plain vanilla decision tree? Can I comment this? Yes, guys. A plain vanilla decision tree or is always having lesser performance, not good performance as compared to random forest. Can I say this, guys? Yes or no, guys? Can we say like that? A plain vanilla random forest is always good than your decision tree model. So that is what your entire thing is, right? So this comes to our discussion of for the next week itself. This itself is the discussion for the next week. I mean, we are starting our discussion for the next week. So it is 11th Jan. And we are going to start the random forest, right? We are going to start the random forest in the next session. So I'll just write down random forest is always a better model than decision tree. Second point I'll write down is you can literally close your eyes and use random forest model on any data set which you get in the industry, right? So it's a personal favorite for all the people out there who are in the industry. They directly use random forest on any, let it be any model out there, right? It will always give you good performance as compared to linear regression, logistic regression, KNN, SVM, and your decision tree model, right? So it is always, it will always and always give you the good performance. But having said that, this is not the only best model, We have other model like XGBoost, GBoost, and AdaBoost. They're far better than random forest. So XGBoost is the ultimate model. Below that we have GBoost, and below that we have AdaBoost, right? XGBoost will be always a top performing model out there. So if you go and see the Kaggle competitions or any competitions out there, the people who actually have won that competition, they are using random forest, and if not random forest, they are always be using XGBoost and winning the competition out there, right? So XGBoost, no matter what, will be ultimate model out there, but still random forest, you don't have to underestimate random forest, right? Now let us discuss the questions. Gopi is asking, sir, when you will discuss about DL architectures for sequence processing, recurrent neural networks in NLP? Yes, Gopi, we are still left with machine learning part, and I don't want to complete this in a hurry. So that's the reason I am going it very slow. Uh, so we have not started the deep learning yet, right? We still require 2 more session to start the deep learning part. We'll just share, I'll just share the syllabus and we'll discuss that point. So that is kept at the last, right? That particular points are kept at the last.
Okay, sir.
Let me just share the syllabus. Yeah, this is your syllabus, right? Try the extension. Yeah. Okay. I'll just share this. All right. All right. So everything is completed till this point of time here. Right. We haven't discussed K-means. See, that's the reason I told they are requested to complete this in 4 days. 1 session, 2 session, 3 session, 4 session. Physically, it's not possible. See, can you relate this fact that for this 2 session itself, logistic regression itself, we have spent more than 2 sessions, right? So see, random forest and dysenteries, not only we should discuss only this topic, we should go beyond this and explore what is necessary. So ideally, it should take 1, 2, 3, 4 at least, 6, 7 sessions, but we are exceeding sessions. That's the reason it is not started yet, neural networks. So uh, the question that you have asked related to recurrent neural network, it is over here. Can you see this? It is in model number 5, deep learning architectures for sequence processing and recurrent neural networks is NLP, right? So don't worry, we are going to discuss this. But I wanted to take this thing as it is very important as well, right? This one. So we are still with this module. We haven't started the neural network yet. Yeah.
So that means
Okay.
after 18 modules also you will discuss that, right?
After 18 modules.
After the completion of 18 modules also you will discuss about these neural networks, right?
Yeah. That's what I'm saying. See, you are getting notification about this, no?
Yes,
That
sir.
we are,
Yes, sir.
see, we have to start this neural network, NLP with neural network. But it's not the case. Like we will require extra session. So that's what I'm talking about.
Okay, sir. Okay, sir.
Yeah. Don't worry, we'll complete everything which is there in your syllabus. All right. Anything else? Yes, guys. Yes, guys, do you have any questions, any doubts? All right, then, perfect. We'll stop here for the day. Thanks for your time. Happy learning and revise this.
So